Hello, my name is Benjamin Lin. Today I will be going over the 2024 USNCO National Exam Part 1 Solutions. This is the second video in a two-part series, so today we will be covering questions 31 through 60. So without further ado, let's get started. Problem 31. A 0.320 mole of a weak monoprotic acid in 1 liter of solution is 10.2% ionized. What is the Ka for this acid? So, this is the dissociation of an acid, so HA. It's in equilibrium with H plus and A minus. And we're told that 10.2% of it is ionized. So we can say that 0.320 moles times 0.102, that's our percent, which comes out to 0.0326 moles of H plus and 0.0326 moles of A minus. And we also know that the amount of HA remaining is going to be 0.320 moles minus the amount that's ionized, so minus 0.0326, and that's going to come out to 0.287 moles of HA. And now, because this is all happening in 1 liter of solution, we know that the amount of moles and concentrations are the same numerical value. So we can say that the Ka for this reaction, which is equal to the concentration of H plus, concentration of A minus over HA, is equal to 0.0326 squared over 0.287. And when you plug this in to your calculator, it comes out to 3.71 times 10 to the minus 3, or B, which is our correct answer. Problem 32. Typically, the molar solubility X of an ionic compound in pure water and its KSP are related by a simple formula. Which formula is not expected for KSP for an ionic compound? So in general, we know that for an ionic compound, let's say the cation C with the subscript M, and an anion A with the subscript N, right? So those are the amounts of each in the species. We know that KSP is equal to M to the M times N to the N times X to the M plus N. So we can see what kind of follows this pattern. 4x cubed is a very common one. Let's say, for example, we have silver oxide, so Ag2O. In this case, M equals 2 and N equals 1. So when we plug into our expression, we get 2 squared times 1 to the 1 times x to the 2 plus 1, and that's clearly 4x cubed. So this is possible and very common, so this cannot be correct. Now for B, it's a little trickier. KSP equals 4x to the fourth. This can actually happen when we have an ionic species with 3 different ions in it, such as like a double salt. So let's say, for example, alum, which is potassium aluminum sulfate, SO4, 2. And in this case, we will have some cation M, some second cation, I'm just going to use D to the N, and then the anion A, which is, I don't know, has subscript P, let's say. And KSP for this type of species will equal M to the M times N to the N times P to the P times X to the M plus N plus P. And then we can just plug in our values. In this case, M equals 1, N equals 1, and P equals 2. So in this case, we have 1 to the 1 times 1 to the 1 times 2 to the 2 times x to the 1 plus 1 plus 2. And clearly this gives us our 4x to the fourth, so this is possible. So B is not correct. C is also another common one that follows this CMAN type of form. And this happens with something such as sodium phosphate, so that would be Na3PO4. In this case, from our expression here, M equals 3 and N equals 1, right? because the phosphate is just one of them. So if we plug into our KSP, we have KSP equals 3 to the 3 times 1 to the 1 times x to the 3 plus 1. And this is obviously 27x to the 4th. So this is possible. And that leaves us with D, which is not possible. Problem 33. Equal volumes of 0.1 molar solutions of NaH2PO4 and Na3PO4 are mixed. What is the pH of the resulting solution? And then they give us the pKa values. So in this case, the major equilibrium we're going to be talking about is this H2PO4 minus and the PO43 minus in equilibrium, where the H2PO4 minus protonates the PO43 minus, creating 2 HPO4 2 minus. Now, if you're familiar with the pH equals the average of the pKa trick, we can plug that in here. So pH equals 1/2 times, in this case, it'll be pKa 2 and pKa 3, because those are the relevant equilibria. And then if we plug in the values 7.21 and 12.32, we get 9.76, which corresponds to D. Now, if you're not familiar with this trick, or even if you are familiar with this trick, it's important to know where it comes from and how to derive it. So let's just go through that really quickly. So we know that Ka2 for phosphoric acid is going to be equal to the concentration of HPO4 2 minus times the concentration of H plus, all divided by the concentration of H2PO4 minus. We also know that Ka3 equals the concentration of PO4 3 minus times the concentration of H plus times divided by the concentration of HPO4 2 minus. If we multiply Ka2 and Ka3 together, the numerator here and denominator here are going to cancel out, so that's going to leave us with Ka2 times Ka3 is equal to the concentration of H plus squared times the concentration of PO4 3 minus, and then that all divided by H2PO4 minus. Now, what we can do is, based off this reaction stoichiometry, right, we can kind of assume that the concentration of H2PO4 minus and the concentration of PO4 3 minus are approximately equivalent to each other, because they're added in equal concentrations and volumes, and they will, when they react in a 1-to-1 ratio. So we can say that these two are approximately equal, and as such, we can cancel out these two terms. And therefore, we can say that Ka2 times Ka3 is approximately equal to the concentration of H plus squared. If we take the negative logarithm of both sides, we have negative log of Ka2 times Ka3 equals negative log of the concentration of H plus squared. And then we can just use our log rules to simplify down to our final equation. So this becomes pKa 2 plus pKa 3 equals 2 times pH. And if we divide both sides by 2, we get our final expression where pH equals the average of pKa 2 and pKa 3. So we know our equation works. Problem 34. 5 grams of nitrogen dioxide is introduced into an evacuated rigid 1-liter container. It is allowed to equilibrate according to the reaction below at 310 Kelvin, and the total pressure in the vessel is 1.71 bars. What is the Kp for the reaction at 310 Kelvin? So to start, we should figure out how much nitrogen dioxide is added in terms of pressure. So we can do that by finding the amount of moles of NO2 and then converting that to pressure with the reaction conditions. So we know that 5 grams, and then we're dividing it by the molar mass of nitrogen dioxide, which is 46.01 grams. And this comes out to 0.109 moles of NO2 that we're adding to the reaction vessel. Then, to figure out what the initial pressure of NO2 is, we can use the ideal gas law. So pressure is going to equal nRT over V, and that's going to equal 0.109 moles times 0.08314, which is our gas law constant, times the temperature, which they told us is 310 Kelvin. And this all divided by the volume, and that's a 1 liter container, so it's 1.00 liters. And that gives us our initial pressure of NO2, which comes out to 2.80 bar. Now, knowing the initial pressure of nitrogen dioxide, we can find the final partial pressures of nitrogen dioxide and N2O4. So what we can do is write some expressions. We have pressure of N2O4. Let's just arbitrarily decide that that's going to equal X. Based off of the reaction stoichiometry, we know that for every bar of N2O4 formed, we lose 2 bars of NO2. So we can write an expression for the final pressure of NO2 as the initial, which is, what do we say, 2.080 bar, and then minus 2 times the amount of N2O4 that's formed. Now, we also know that the total pressure, by Dalton's law, is equal to the partial pressures of the components. In this case, that's N2O4 and NO2. And we're also given that the total pressure is 1.71 bar. So 1.71 bar is equal to X plus 2.80 minus X, or minus 2X. When we do the math, we find that X comes out to 1.09 bars. And then if we plug that in to this equation and this equation, we know that the pressure of N2O4 at the end is equal to 1.09 bar, and pressure of NO2 at equilibrium is equal to 0.62 bar. So we know Kp equals pressure of, what is it, NO2? NO2 squared divided by pressure of N2O4, and that's going to equal 0.62 squared over 1.09, and that comes out to 0.35. So A is our correct answer. Problem 35. A mixture containing carbon monoxide, water, carbon dioxide, and hydrogen gas is allowed to reach equilibrium at 120 degrees Celsius in a container that maintains a constant total pressure of 1.0 bar. So 5 grams of water is added to this container, which is allowed to reattain equilibrium still at 120 degrees C and 1 bar total pressure. How does the partial pressure of H2 change as a result of the addition of H2O? Because we're not given any information about the equilibrium constant, we need to consider the two cases where K is very small or K is very large. And then we know the real equilibrium will lie somewhere in between that. So we know for case 1, K is very small. We can say that K is approximately equal to 0. And by adding any reactants to the reaction vessel, we're not going to create any more product if K is nearly 0. So if there's more species in the reaction vessel, the mole fraction of H2 is going to go down because we didn't create any more H2, and we're increasing the amount, total amount of moles in the reaction vessel. So as such, we would expect the partial pressure of H2 to decrease. The second case is where K is very large, nearly infinity. And in this case, adding any more reactant, assuming that water is limiting, is going to just create more products, right? It's going to use up this reactant and just create more products. And as such, we would expect the mole fraction of H2 to increase. If the mole fraction of H2 increases and the total pressure is the same, that means we expect the partial pressure of H2 to increase as well. So because we're getting conflicting data based on whether or not K is small or very large, and we have no information about the real value of the equilibrium constant, we cannot tell whether or not the partial pressure of H2 will increase or decrease only from the information given. So D is going to be our correct answer. Problem 36. 0.01 moles of silver nitrate is dissolved in 1 liter of 1 molar aqueous ammonia. What is the minimum amount of hydrochloric acid that would need to be added to the solution to induce precipitation of silver chloride? And then they give us a bunch of equilibria. So whenever we have a lot of simultaneous equilibria that we need to solve together, instead of resorting to some mass charge balance type of solution, we can usually make some assumptions that will help us simplify the process significantly. Each of the equilibrium constants can help us with one of the assumptions. So the first one, KSP of silver chloride, is 1.8 times 10 to the negative 10. This is a very small number. So we know that if we're adding a non-negligible amount of chloride, the chloride is basically going to control the concentration of silver that's in solution. So we know that KSP, for example, is equal to the concentration of silver plus times Cl minus. And because we know that this is so small, we know that effectively the concentration of silver plus is going to equal the KSP divided by Cl minus. And in a way, we know that the chloride concentration, whatever we add, is going to control the silver concentration. And then our second assumption is going to be that because this formation constant of this complex is so large, whenever there's any silver in solution, so silver in solution, it immediately forms this complex. So we're going to create this AgNH3 2 plus complex. And what this tells us is, because we added 0.01 moles of silver nitrate in 1 liter of solution, the concentration of this complex is approximately equal to 0.01 molar, because all of the silver is present as this complex. Our last assumption comes from the Ka of NH4+. So we know that the Ka of this acid is very small. As such, we know it's a very weak acid, and its conjugate base is going to be relatively a decent base. So we can say that any NH3 in solution will grab available protons from the HCl. So if we say that we're adding X moles of HCl in solution, we can describe our expressions as follows. So from the first equation, we know that silver plus is equals to KSP divided by X, because that's how much chloride we're adding. The second expression stays the same, so this is going to be AgNH3 2 plus. So this is approximately equal to 0.01 molar. And we know that the concentration of NH3 is equal to whatever its initial was, which was, what, 1 molar? 1 molar minus X, because for every HCl that's added, we're decreasing the concentration of NH3. Now you can just plug everything into the equation for the formation constant of the complex. So we know Kf is equal to the concentration of silver NH3 2 plus divided by the concentration of silver plus and NH3 squared. All right, now we can plug in our expressions. So we have this approximately equal to 0.01 divided by our concentration, or our expression here. So this is KSP over X, and then times 1 minus X squared, because that's our NH3. And then if we use our calculator to solve for X and we plug in a value for KSP that we're given, the number comes out to 0.19 moles HCl. And looking at our answer choices, this is very close to C. So not bad for a lot of assumptions that we made. Problem 37. In which compound does the oxidation number of oxygen differ from -2? So let's just look at all the anions first. This is a weird one, BO3. I'm not familiar with it. And then there's nitrate, phosphate, and dichromate. Nitrate, phosphate, and dichromate are all common ions that don't have oxygen in weird oxidation states. So we know immediately that these are not correct. So we know A is the correct answer. But let's consider how we could figure this out if we didn't know that nitrate, phosphate, and dichromate are all common anions with oxygen as a -2. So we know that sodium as an alkali metal is going to have a +1 state. That means the rest of the molecule, BO3, must have -1 because overall it's neutral. And let's imagine that each of the 3 oxygens were in -2. That means in total they would have a -6 oxidation state, implying that boron would have a +5 oxidation state. Now let's consider if that's really feasible. We can turn to the periodic table to help us out. Now boron is right here with its electron configuration of 1s2, 2s2, 2p2, 2p1, sorry. In order for boron to be in a +5 oxidation state, it's going to need to lose its 2p electron, its 2s electrons, and its 1s electrons. Losing the 1s electrons is very energetically unfavorable because those are core electrons very close to the nucleus, so we don't expect it to be energetically feasible for boron to be in the +5 oxidation state. Instead, boron will adopt a +3 oxidation state, so losing its 2s2 and 2p electrons, but keeping its 1s2 electrons intact. So now we know that boron can't be in +5, and instead it's going to be in +3. We can say that the oxygens together, those three of them, the O3, is going to have to add up to -4 because the overall is still -1 like we just discussed. So therefore the average charge for each oxygen is going to have to be -4/3, and that's clearly not 2. So we know that this A is correct. Problem 38. Copper metal reacts with nitric acid to form NO gas, as shown in the unbalanced reaction below. When the reaction is balanced using lowest whole number coefficients, what is the coefficient of H+? So in the written annotations, I use the half reactions method, but here I will show you a different and, in my opinion, much faster alternative. I will make a separate video dedicated to just this method of balancing redox equations, so I'm going to kind of speed through it here. Hopefully it's familiar to some of you. So let's just write out the reactions first, not including the acid and water. So we have copper and the nitrate ion going to copper 2+ and NO gas. In this case, the atom being oxidized is copper, so it goes from 0 to +2. And the atom being reduced is nitrogen, so it goes from +5 here to +2 here. Overall, copper gets oxidized by 2 oxidation states, and nitrogen gets reduced by 3 oxidation states. The least common denominator of 2 and 3 is 6, so we can multiply the reaction stoichiometry to get to 6. So we get 3Cu plus 2NO3- goes to 3Cu2 plus 2NO. Now we can just balance the charges. There's 6+ on this side, 2- on this side. That means we need to add H+ to the left side, and it's going to be 8 of them. So it's going to be 3Cu plus 2NO3- plus 8H+, and then that yields 3Cu2 plus 2NO. So then we just need to balance the hydrogens. On this side, we have 8 hydrogens, so we're going to need to add 4 waters to this side. And we're done. We successfully balanced the equation. If you want to check your work, you can look at the number of oxygens. So there's 2 oxygens here and then 4 here. So there's 6 oxygens on this side. On this side, only oxygens come from here and there's 6 here. So we balanced it correctly. So the question is asking us what is the coefficient of H+, and that's going to be D. Again, I'll make a separate video dedicated to this method because it's very helpful in my opinion, and there's more to it than shown in just this example. Problem 39. In the Hall-Héroult process for producing aluminum, aluminum is electrolytically reduced from Al2O3, dissolved in molten cryolite, which is this, while a graphite anode is oxidized to CO2. What is the ratio of the mass of Al deposited on the cathode to the mass of C lost from the anode? So I think the best way to start this problem is by writing out the balanced redox reaction. We are told that Al2O3 is reduced electrolytically, so it's a reactant. So Al2O3 is reduced, and graphite, the anode, is going to be oxidized, so plus C. And the products are going to be the aluminum that we're looking for and the CO2. And then now I'm going to use the method I just talked about to balance this equation. So I'm going to put a 2 in front of the Al first to balance the atoms on both sides. And then what I'm going to do is the same thing as before. So each of these oxygens contributes a -2. So that means together that these 2 aluminums are going to have to be +6. This carbon's obviously 0. And these are 0 as well. And this carbon is +4 because these 2 are both -2. Now we need to balance it. So we have here the change is -6, and here the change is +4. What's the least common denominator of 6 and 4? That's going to be 12. So that means we're going to need to multiply this by 2, Al2O3, and this by 3, so plus 3C goes to, now we multiply this by 2, 2 times 2 is 4, 4Al, plus, what's it, 3CO2. Now that we've balanced the redox equation, based off the stoichiometry between aluminum and carbon, we can figure out the ratio of mass that they're asking for. We know that for every 4 moles of Al produced, there are 3 moles of carbon used up. Now if we want to know the ratio of the masses, like the question asks us for, we can multiply by the molar masses. So we have 4 moles of aluminum times, I believe, 26.98 grams of aluminum, grams per mole. And then that's going to be divided by the 3 moles of carbon times the 12.01 grams per mole. And then when you compute this ratio, you get approximately 3. And so we have a 3-to-1 ratio of aluminum mass produced to carbon mass used up, and therefore C is our correct answer. Problem 40. The cathode of an electrolytic cell with a copper electrode has 100 mils of a solution that is 1 molar in both copper 2+ and this iron cyanide complex. The solution is electrolyzed with a constant current of 0.5 amperes at a constant temperature of 298 Kelvin. How much time elapses before Cu starts to deposit on the electrode? First, it's best to understand what's going on. So in the cathode, we have both this iron cyanide complex and this Cu2+. And both of them are candidates to be reduced. The reaction is going to reduce the one that is more spontaneous to reduce, and the way we know which one's more spontaneous is by its cell potential. Because both of them are initially at 1 molar, we can say both of them are initially at standard state, and as such, clearly the iron cyanide complex has a higher reduction potential and is going to be reduced first. What the question is asking us is when does the copper start to get reduced? And that is going to be when the iron cyanide complex gets reduced so much that its reduction potential falls to be equal to that of the copper. So we can use the Nernst equation to help us out. We know that 0.337 is the final voltage we're trying to get to, and that's going to be equal to the initial voltage, 0.370, minus RT over NF, so RT over NF, times the natural log of Q. And if you plug in the values for RT over NF, for n equals 1, you're going to get 0.0257. We also know that Q, the reaction quotient, Q is equal to, in this case, it's going to be this species over this species. So it's going to be concentration of FeCN 6,4 minus FeCN 6,3 minus. And let's just set an arbitrary variable to x, which is equal to the concentration of FeCN 6,4 minus. If this is equal to x, and we know that initially that this complex starts at 1 molar, we can say that the concentration of FeCN 6,3 minus is equal to 1 minus x. So we can plug all of this back into our equation. We get 0.337 equals 0.370 minus 0.0257 times natural log of x over 1 minus x. If we solve for x, we get x is equal to 0.783 molar. In this case, we are working with 100 mils of solution, so 0.783 molar is equal to 0.0783 moles of reaction. We also know in this case that the moles of reaction is equal to the moles of electron because only 1 electron is used per reaction. So we can use dimensional analysis to figure out how long this will take. So we have 0.0783 moles of electrons, and we know 96,500 coulombs for 1 mole of electrons. And we're also given the amperage, which is 0.500, so that's 0.500 coulombs per 1 second. And then they're asking us in terms of minutes. So we just take 60 seconds for 1 minute, multiply this all out, and the value you get is 252 minutes, which is our answer. So C is correct. Problem 41. A molecule absorbs a photon of light to form an excited state. How do the redox properties of the excited state compare to those of the ground state? Now, we have some compound in its ground state. Its electrons are all going to occupy the lowest energy molecular orbitals. So let's say this is an energy diagram. When we undergo some sort of excitation with light, we're going to have the electron jump to a higher energy level. So it might maintain its spin or flip its spin, but that is completely irrelevant to this question. Now the question asks us to compare the redox properties of each of these states. So what does it mean to be an oxidizing agent? Well, that means you're accepting electrons. Now which one do you think is going to be more spontaneous? If we're accepting an electron in a high energy molecular orbital like this, or we're accepting an electron in a lower energy molecular orbital like this? Well, clearly, it's going to release more energy when we go to a lower energy molecular orbital because that electron is going to be more stable. So this excited state is going to be a stronger oxidizing agent. And what does it mean to be a reducing agent? Well, what that means is how well you can donate electrons to another species. If you would imagine, this electron up here is a higher energy electron than this electron down here. If the electron is higher in energy, it's easier to remove from the atom to be donated to another electron. As such, it's going to also be a stronger reducing agent. Because its electron is higher in energy. Therefore, we can say that the answer is A. Problem 42. What is the delta G naught at 298 Kelvin for the disproportionation of lead oxide? So this is just going to be a standard type of Hess's law problem. And you just need to figure out the right combinations of reactions to add together, and then you'll figure it out. I've already worked that out for you, but I'll prove it to you. It's going to be 2 times this reaction, and then minus 1 times this reaction, because it's going to be the reverse. And then we're going to add something to do with the autoprotolysis of water. So it's going to be 2 times this bottom reaction, so that's going to be 2 PbO plus 2 H2O plus 4 E minus, and that's going to yield 2 Pb plus 4 OH minus. Now if we add the reverse of this reaction, we're going to have Pb plus 2 H2O, and that's going to yield PbO2 plus 4H plus 4E minus, and then we're going to add the reverse of the autoprotolysis of water, so that's going to be H plus OH minus, and that's going to go to water, and then we're going to need to multiply this reaction by 4, so we have 4H plus, 4OH minus, and 4H2O. Now, just so I can prove to you that everything works out, when we add these together, the lead here is going to cancel with this coefficient right here. The 2 waters are going to combine to 4 waters, so this becomes 4. The electrons are going to cancel out, and then the 4H plus, the 4H minus are going to cancel out here, and the 4 waters are going to cancel out with this 4 waters. So we end up with 2 PbO goes to Pb plus PbO2, which is exactly what the question is asking us for. Now we just need to calculate the delta G values for each of the reactions we summed up together. So the first reaction is going to be this one, and then multiply by 2. So we know that delta G naught equals negative NFE naught. And then in the reaction multiplied by 2, there's going to be 4 electrons. So we have negative 4 times 96,500 coulombs per mole electrons times E naught, which is negative 0.580. Right. We also know that we're adding a reverse of this reaction. The reverse of this reaction is going to have the opposite standard cell potential. So that's going to be delta G naught, again, equals negative NFE naught. And that's going to equal negative, in this case, still 4 electrons, times 96,500. And then the negative of this cell potential, which is negative 0.671. Finally, for water, we know its Kw value. So Kw corresponding to water going to H plus and OH minus. The K value for the reverse reaction multiplied by 4 is going to equal Kw to the negative 4. So for this reaction, H plus 4H plus plus 4H2O. And that's what we added right here. To calculate delta G naught for this reaction, we use our negative RTL and K. So delta G naught, and this is going to be equal to negative 8.314 times 298 Kelvin times natural log of K for this expression, which is Kw times to the minus 4. And if we plug in all the values into our calculator and add delta G naughts for this, this, and this together, we will find delta G naught for our desired reaction right here. And that's going to come out to 163.4 kilojoules per mole when you convert back to kilojoules. And that's going to correspond to A. So A is correct. Problem 43. For which gas phase atoms is addition of an electron endothermic? For most elements, adding an electron is going to be exothermic because you're bringing a negative charge closer to a positive charge, which is stabilization and a loss of energy. But there are some exceptions. The notable ones are beryllium, magnesium, nitrogen, and the noble gases. To understand why these elements are exceptions, we need to look at their electron configurations. For nitrogen in particular, we have the 2p orbital that is half filled, like so. And half-filled subshells are relatively stable because none of the electrons are in the same orbital and they don't experience those electron-electron repulsions from each other. Now, if we add another electron, like so, there will be an associated pairing energy because of the electron-electron repulsions. And this actually makes it energetically unfavorable for you to add an electron to nitrogen, and that's why it's endothermic. So in this case, it's going to be B only. And if you're more interested in pairing energy, the explanation is more complicated than just electron-electron repulsions, but I think that suffices for now. Problem 44. Which atom has the lowest first ionization energy? So between these options, we know that beryllium and boron are in period 2. Because they're in period 2, their highest energy electrons are in n equals 2, and that's what we know from them. Magnesium and aluminum are period 3. So their highest energy electrons are in n equals 3. N equals 3 electrons are higher than 2 because they are further away from the nucleus. So we expect that the ionization energies for magnesium and aluminum are going to be lower than that for beryllium and boron. So it's not going to be A or B. Now, between magnesium and aluminum, when you're ionizing from magnesium, you only have the 2s2 electrons to work with. So you need to take out a 2s electron. For aluminum, you have the 2s2 electrons and the 2p1 electron. The 2p electron is going to be higher in energy than the 2s2 electrons of magnesium. Therefore, it's easier to ionize, and aluminum has the lowest ionization energy. Problem 45. How many electrons in a ground state gas phase atom of arsenic has a quantum number of m sub L equals 1? So we know m sub L has the range from negative L to positive L. And in order for m sub L equals 1, that means L must be greater than or equal to 1. So what does this tell us about the orbitals? This means that we are not referring to the s orbitals, but we have p, d, f, and everything later on as orbitals we can consider. For every complete p orbital, or d orbital, or f orbital, we're going to have 2 electrons. And then if there's a half-filled subshell, we're only going to have 1 electron. Now let's look at arsenic in the periodic table. So arsenic is right here. We can tell that it has a complete 2p orbital, has a complete 3p orbital, and it has a complete 3d orbital. And as we just said, 2 electrons come with m sub L come from each of these electrons, so this is 6 electrons. And then here we see that it has a half-filled, right? Half-filled 4p electrons. So therefore, it's going to add 1 more electron, and our total is 7 electrons. So B is our correct answer. Problem 46. Which orbital has the same number of radial nodes as a 3s orbital? So we know the formula for radial nodes, so let's just call that R, is equal to the principal quantum number n minus 1 minus the angular momentum quantum number, which is L. Now for 3s, 3s we're going to have equals 3 minus 1, and for an s orbital, L equals 0. So minus 0, and that equals 2. So then we just need to plug in values for each of these. For 3p, we're going to have 3 minus 1 minus 1, and that's equals to 1, so that's clearly wrong. For s, we're going to have 4 minus 1 minus 0, and that's going to equal 3. That's not equal to 2, so no. For f, we have 4 minus 1 minus s is p, d, f, so 3. So that's going to equal 0. That's not correct. So we know D is our correct answer. So to prove that, we have 5D. So we have 5 minus 1 minus 2, and that comes out to 2, which matches the same thing as 3s. So therefore, D is correct. Problem 47. Which lanthanide has a common oxidation number different from +3? This is kind of a trivia question. The answer is going to be cerium, because it can also have the common +4 oxidation state. If we didn't know that, we can kind of justify this from the periodic table. So let's look at that. We have cerium here. And if it was in its +3 oxidation state, it would lose this electron, and this electron, and it would have this one extra electron left over. And we can imagine ionizing this last electron is not crazy difficult, because doing so would lead us to the pseudo-noble gas configuration for xenon. So we can expect that cerium will have a +4 oxidation state as well as +3 oxidation state. Therefore, A is correct. Problem 48. Which radioisotope decays by beta minus emission? So in beta minus emission, what we have is a neutron, and it decays into a proton and loses its beta minus particle, which is an electron. So in the process, what happens is the proton count goes up, and atomic mass stays the same. It doesn't change. So we need to consider which one of these isotopes that would benefit. We can use the periodic table to help us out. So for sodium-20, for example, sodium usually has a molar mass close to 23. However, something like neon has a molar mass closer to 20. So what we want to do is actually lose a proton and turn it into a neutron, so we can decrease the atomic number while maintaining the mass as the same thing. However, beta minus decay actually does the opposite. It increases the proton count while keeping the mass the same. So that's not going to be what we want. Now, for vanadium-52, vanadium has a molar mass usually of around 51. If we increase this proton count, it would go to chromium, and its mass would stay the same. It would still be 52. And that's clearly what chromium is supposed to be like, based off of the value on the periodic table. So we know vanadium is going to be our correct answer. Now let's consider the others, just to be sure. Cobalt, 54. Cobalt has a molar mass closer to 59, and nickel is something similar. Increasing the proton count will not help us, because we're still not getting closer to the observed molar mass that we get. Now for copper, if we increase the proton count, we get to zinc. And zinc also does not have a molar mass close to 62, so this is not favorable either. So we know that the answer definitively is vanadium. B is correct. Problem 49, which is a valid Lewis structure for nitric acid? HNO3. So we know nitrogen is a period 2 element, so we would expect it to follow the octet rule, meaning that it cannot have more than 8 electrons around it. And in this case, that's enough to find the correct answer. Here, we have 1, 2, 3, 4, 5 bonds around nitrogen. Each bond is 2 electrons. That's 10 electrons on the nitrogen. So this does not follow the octet rule. A is wrong. For B, we have 2, 4, 6, 7 bonds, which is 14 electrons. Still violates the octet rule, so B is wrong. This one, we have 1, 2, 3, 4, and that's going to be 8 electrons. That does follow the octet rule, so C is definitely a possibility. And then D, we have 1, 2, 3, 4, 5 bonds, which again is going to be 10 electrons around the nitrogen, which does not follow the octet rule, so this is wrong. C is correct. Problem 50. Which statements about carbon-oxygen bond lengths are correct? 1. The carbon-oxygen bond length in carbon dioxide is shorter than the carbon-oxygen bond in carbonyl sulfide. Let's draw the resonance structures to help us out. So for CO2, we have COO, and then we have nice double bonds here and a double bond right here. Now, for COS, we have something very similar, where we have something like this and like this. And there's actually another resonance structure for this, which looks like this. So O, S, so this will be minus and this is plus. And in this case, actually this is a major resonance contributor. And why is that? Well, it's actually because sulfur forms very weak double bonds with other elements. This is true of period 3 elements and later, because their p orbitals are so large in size that there's poor overlap. So we know that this is actually a major contributor. If this is a major contributor, that means the carbon-oxygen bond has a bond order between 2 and 3. And if it's somewhere between 2 and 3, we expect that its length is going to be shorter than a bond with the bond order of just 2. So therefore, we would say that the carbon-oxygen bond in carbon dioxide is actually going to be longer than the bond in COS. So therefore, 1 is incorrect. 2, the carbon-oxygen bond in phosgene is shorter than the carbon-oxygen bond in urea. So let's draw the structures of phosgene and urea, just like we did before. So we have this carbon, double oxygen, chlorine, chlorine, and this carbon double bond oxygen. If you're familiar with amides or urea groups in organic chemistry, you'll know that there's a major resonance contributor like so, where we have the carbon-oxygen actually as a single bond, and a nitrogen like so, with a positive formal charge, H2. And we know that the carbonyl bond length, this carbon-oxygen bond, is actually going to be somewhere between 1 and 2, bond order, is going to be somewhere between 1 and 2. Therefore, the bond length is going to be longer than that of a pure C double bond O. A pure carbon-oxygen double bond is something we almost observe in phosgene, at least much more so than urea. So therefore, we can say that the carbon-oxygen bond in phosgene is shorter than the carbon-oxygen bond in urea. So therefore, 2 is correct, and our answer is B, 2 only. Problem 51. Which statement best describes the relative Lewis acidity of BF3 and BCl3? So in general, we're going to have this type of Lewis acid. So we have a boron and some X halogen, some other halogen, and the same halogen over here. And the boron is going to have an empty p orbital, like so. A Lewis acid is a compound that accepts electrons, and the boron compound that's going to accept electrons best is going to be one where the boron is electron poor. Now, there's two effects here. So a halogen is electronegative. And because it's electronegative, it's going to withdraw electron density from the boron center. Right? It's going to withdraw electron density. This is going to increase its Lewis acidity. Now we're comparing BF3 and BCl3. Well, fluorines are more electronegative than chlorines, so therefore they're going to more effectively withdraw electrons from the center by induction. So this might lead you to believe that BF3 is stronger Lewis acid. So we don't know for sure, but that's what we think. Now, there's also a second effect that we cannot forget about. These halogens are going to have their p orbitals, like so, and electrons in their orbitals. And what happens is, this is a sort of conjugation where the electrons are donated back to the boron center, increasing the amount of electron density around the boron and decreasing the effective positive charge there. So how do we compare fluorine and chlorine? Well, fluorine is a n equals 2 type of atom, and chlorine is a n equals 3. The 2p orbitals on fluorine are more effective donors to the 2p orbital of boron because they're similar in energy and size, as opposed to the 3p orbital of chlorine is not going to donate well to the 2p orbital of boron because it's bigger and has a different energy level. Therefore, we expect that BF3 is actually a weaker Lewis acid, as its boron is more electron rich. So which of these effects is going to dominate? Well, in general, resonance effects, like hyperconjugation or back donation, like what's going on right here, tend to dominate over inductive effects. And this is something you would learn in organic chemistry. So as such, we would expect this type of effect to dominate. And in this case, BF3 is a weaker Lewis acid. So looking at our answer choices, we know that B is correct because it says that BF3 is a weaker Lewis acid, and it's because that F is a better pi donor than chlorine, right? It's a better donor of electrons back to the boron center, which matches our analysis. So B is correct. Problem 52. Which comparison of bond angles are correct? 1. The bond angle in NH3 is greater than the bond angle in NF3. 2. The bond angle in NH3 is greater than the bond angle in pH3. So for the first question, what's going to be relevant to us is this concept called Bent's rule. Bent's rule states that more electronegative elements will have less S character in their bonding orbitals. So in this case, we're comparing fluorine and hydrogen, because that's the difference between NF3 and NH3. And we know that fluorine is much more electronegative. As such, its NF bonds will have less S character. And hydrogen, its NH bonds, will have more S character. So what does this S character really imply about everything? Well, we know that, for example, sp3 has an ideal bond angle of 109.5. sp2 has an ideal bond angle of 120. And sp has an ideal bond angle of 180. And we notice that in an sp3 orbital, there is one s orbital and 3 p orbitals. That means an s character of 25%. Here, s character is 33%. And here, s character is 50%. And we notice the trend here, right? As we increase the s character, we're also increasing the bond angle. Now, NF3, we say that we'll have bonds with less s character. Therefore, we expect that its bond angles are actually going to be smaller than those of NH3. Therefore, we know that 1 is correct. No. Statement 2 asks us to compare the bond angles of NH3 and pH3. So what we need to really compare is nitrogen and phosphorus. Nitrogen is able to hybridize into sp3 very effectively. However, phosphorus is not able to do the same nearly as well. And this is generally what we observe as we go down the periodic table. Why is this? So for nitrogen, its 2s and 2p orbitals are very similar in energy. Therefore, they can mix effectively and create these hybrid orbitals. However, for phosphorus and the later elements, the difference between the s orbital and p orbital energy continues to grow. Therefore, effectively, we have just an s orbital and 3p orbitals. And the 3p orbitals are going to be what is used to bond to the hydrogens. The s is going to be the lone pair on the phosphorus. Now, if we're comparing the bond angles of sp3, that's going to be 109.5 degrees. And the p orbitals, which are all orthogonal to each other, those are going to have 90-degree angles to each other. So the pH3 bond is going to be much more close to something like 90 degrees, while NH3 is going to have bond angles closer to 109.5 degrees. Therefore, we can say that the bond angle in NH3 is in fact greater than the bond angle in pH3. So statement 2 is also correct, and C is our correct answer. Problem 53. The gas phase molecules of B2 and O2 are both paramagnetic. Which statement about the relative energies of their molecular orbitals explains these observations? So it's best to draw out the molecular orbital diagrams for B2 and O2. So I'll do that first. So for B2, we have the 2p. With the molecular orbital diagrams drawn out, we can look for our answer. So statement 1 says that the sigma 2p molecular orbital is higher in energy than the pi 2p molecular orbitals. And this is exactly what we observe for B2. And it's the reason why it is paramagnetic. Because if we imagine that instead the sigma 2p was below the pi 2p, and then both electrons would occupy the sigma 2p, and they would both be paired to each other, and the compound would not be paramagnetic. So therefore, this is correct for B2. Now for 2, the sigma star 2p molecular orbital is higher in energy than the pi star 2p molecular orbitals. Now, this is true for oxygen, and this is the reason why it's paramagnetic, because if the opposite were true, where the sigma star 2p was lower in energy than the pi star 2p, then both of these final electrons here would occupy this molecular orbital. And that would give us, again, paired electrons, not giving us a paramagnetic compound. So this is true for oxygen. Therefore, we can say that A is our correct answer. Question 54. How many stereoisomers are there of the octahedral coordination complex, cobalt, and then this bidentate ligand? So this is really a question about facial and meridional isomerism, or also known as FACMER isomerism. The facial isomer is going to be when we can draw all three atoms that are alike in the same plane. So we have the O here, and the O behind it here. And you can imagine that there's a plane that goes through all of these atoms, like so. I'm going to remove that now just for clarity, but that's why it's called the facial isomer. And then we're going to actually have the nitrogens like this, and the compound is going to look something like this. So here, here, and here. And then we also have the mer isomer, the meridional isomer. And that's going to be where all of the same atoms lie in like a meridian, if you imagine on the globe. So let's just do that for oxygen. So we would have an oxygen here, an oxygen here, and an oxygen here. And this would be the meridian, if you imagine a sphere around the complex. But let's just remove that for clarity. And then the nitrogens will occupy the other spots. So we'll have a nitrogen here, a nitrogen here, and a nitrogen here. And again, we're going to have bonding like so. So this is the FAC isomer and mer isomer. Now you'll have to notice that the facial and meridional isomers are actually both chiral here. So there's this isomer is going to have its enantiomer. So in total, there's going to be two facial isomers, and this one's going to have an enantiomer. So there's going to be two meridional isomers, and in total, there's going to be four stereoisomers of this octahedral complex. Problem 55. How many tertiary alcohols have the formula C5H12O? I'm probably going to make a separate video dedicated to isomer counting, but I'm going to show the method right now. So first, we notice that the double bond equivalent is equal to 0 because we have 2n plus 2 hydrogens for 5 carbons. So our expected 12 hydrogens are here. And then, so basically what that tells us is there's no rings and there's no pi bonds. So then let's draw the minimum structure we need to create this tertiary alcohol. So a tertiary alcohol is going to be one like this, where the carbon it's connected to is also connected to 3 other carbons. So it's 1, 2, and 3. And if this carbon is connected to 3 other carbons, that means we already used up 4 of our available carbons. Now, our last carbon we have to attach somewhere. We can't attach it to the oxygen because it already has its 2 bonds. And then we can't attach it to this carbon because it already has its 4 bonds. So we would have to attach it to one of these carbons. So this would give us something like so. Now, if you notice that all 3 of these carbons are chemically equivalent, it doesn't matter where we add the final carbon, they're all going to give the same compound. So therefore, there's only one isomer of this chemical formula that is a tertiary alcohol. Therefore, A is correct. Problem 56. Which difluorocyclohexanes are optically active? So the easiest way to solve a problem like this is convert it back to a normal type of projection, or you can use a Hallworth projection, but I'm just going to draw it as usual. This compound right here has one fluorine pointing up and the other fluorine pointing down, so we can draw it like so. And here. And if you notice, this compound does not have any plane of symmetry and it does not have an inversion center. Therefore, it is chiral and optically active. This compound, on the other hand, has one fluorine pointing down and the other one is also pointing down. So the compound actually looks like this. And we'll notice that there's actually a plane of symmetry now that goes through the molecule like this. So this must be achiral. and is not optically active. Therefore, we could say only one is optically active, and A is correct. Problem 57. Which best describes the outcome of extracting a dilute solution of benzoic acid in diethyl ether with 5% aqueous sodium bicarbonate? So what we have here is a reaction vessel or container with our benzoic acid, let's just call it HA. And then it's all in this ether solvent. We add water and our bicarbonate, so let's just call that base. What it's going to do is deprotonate the HA. So HA is going to go and become a minus. In this case, this is the benzoate ion. And what do we know about benzoate? Well, because it's an ion, it prefers to be an aqueous solution because ions can then be stabilized and solvated by the polar water molecules. So we expect the benzoate to appear in water. Now, looking at the answer choices, the question does not ask you if it appears in water or the ether layer. It asks you if it appears in the bottom or top layer. Well, as a general principle, organic solvents are less dense than water, so they will appear above water, right? So we have the organic layer and then water. And this holds true in most cases, except when the solvent is halogenated, like DCM, dichloromethane, or chloroform, like CHCl3. But ether does not fall in this category, so we're going to have something like this. So as we said, we're going to have benzoate, and it's going to appear in the water layer. And in this case, water is on the bottom. Therefore, we're expecting the benzoate ion to be present in the bottom layer, and B is our correct answer. Problem 58. Which product would be obtained in the greatest quantity from bromination of 4-nitrotoluene using an aluminum bromide catalyst? So this is an electrophilic aromatic substitution, in particular bromination. And we just need to know the regioselectivity of the groups on here. So the methyl group is a weakly activating group, and it's going to be ortho-para-director. So it's going to direct compounds here and here. And then the nitro group is a strongly deactivating group, and it's going to be a meta-director. So it's going to direct here and here. So the most likely spot for bromine to come and attack is going to be right here. It can't attack right here because the nitrogen is already on there, so this is not possible. And as such, we're going to expect that B is our correct answer. If you're not familiar with this reaction, I encourage you to read in on electrophilic aromatic substitution. Problem 59. Which compound is least reactive towards ethyl magnesium bromide? CH3CH2 MgBr. So ethyl magnesium bromide is a Grignard reagent. Grignard reagents are strong nucleophiles. And they attack places with that are strongly electrophilic, which means that they don't have a lot of electron density. Whenever there's a carbonyl group in particular, this carbon is actually very susceptible to attack by the Grignard reagent because it has a significant slightly positive charge as the oxygen withdraws electron density from it. So we already see that A has a carbonyl group, B has a carbonyl group, and D has a carbonyl group, and C does not. As such, we would expect C to be the least reactive with a Grignard reagent, and C is our correct answer. Problem 60. Which statements describe significant differences between RNA and DNA? Statement 1. The bases used in RNA include 3 purines and 1 pyrimidine, while those in DNA include 2 purines and 2 pyrimidines. And statement 2 is, hydrolysis of RNA frequently involves cyclic phosphate intermediates, while hydrolysis of DNA never does. So, to evaluate 1, the first thing we need to do is know what purines and pyrimidines are found in RNA and DNA. RNA and DNA share the same purines, which are adenine and guanine. So that's adenine, guanine. So they both have 2 purines. And then RNA and DNA both actually have 2 pyrimidines as well, but they only share one of them. So they both share cytosine. So this belongs to both. However, only DNA has thymine, and only RNA has uracil. So this is biology knowledge. But in general, both of them have 2 purines and 2 pyrimidines. So this statement is incorrect. One is wrong. For statement 2, we need to know the mechanism of hydrolysis of RNA. So I will draw that for you. So I'm drawing the general structure of RNA here. And now we know in alkaline conditions there's going to be some hydroxide present. And what it's going to be able to do is deprotonate this 2' hydroxyl group. And it's going to give the oxygen and the electrons to attack this phosphorus. And it's going to do this, giving us this type of structure. Like so. And this is the cyclic phosphate intermediate that we're looking for, and it's present in RNA. DNA, on the other hand, actually lacks this 2' hydroxyl group, and therefore cannot undergo this intramolecular nucleophilic attack at the phosphorus, and does not form cyclic phosphate intermediates. Therefore, we can say that B, or 2, is actually correct. And 1 is wrong, therefore B is correct. So that wraps up all of the 2024 National Exam Part 1. I hope you found this informative. Please feel free to leave your questions in the comments because I will answer all of them to the best of my ability. Thank you for watching.